I'm going to do some problems here that have to do with work and energy, and eventually we're going to get into potential energy, which is another way of dealing with some of these things. Start off with a problem here. A chair is sliding across a polished wooden floor with a speed of 3.05 meters per second. It comes to rest after traveling 2.16 meters. What is the coefficient of kinetic friction between the chair and the floor? So keep in mind that friction, if it's kinetic friction, F sub k is going to be that coefficient times the normal force. We could write it in terms of vectors if we want, but we have a relatively simple position here, relatively simple situation. We're going to use the work-kinetic energy theorem to solve this. In this case, well, in every case, the net work that's done on something is equal to the change in kinetic energy. In this case, the work is going to be done by friction. If we just make a little sketch of what's going on here, here's the chair, very crude chair. It's got an initial speed in this direction, and it'll have a displacement in this direction as well, 2.16 meters before it comes to rest. While it's moving, friction is acting on it. If we were to make a free body diagram for this thing, we'd have the normal force upward, mg downward, nothing going on in the vertical direction. It's not jumping off the floor, it's not falling into the floor or through it. And then there's friction that's opposing the motion in this direction. And this is kinetic friction because it's sliding. So the work done by a force when they're along a line with each other or opposite each other is the magnitude of the force times the displacement. In this case, it'll be negative work because the force is acting opposite the displacement, and it'll just be minus F sub k times the displacement. Well, F sub k is mu sub k times n. The normal force in this case is going to just equal mg, and so that frictional force will equal minus mu sub k mg, that's the coefficient of kinetic friction, times the normal force, and then we've got the displacement in here as well. So that's the net work that will be done. That will equal the change in kinetic energy, which is going to be 1/2 mv final squared minus 1/2 mv initial squared. But the final velocity is 0, so this first term is 0, so we'll have minus mu sub k mgd is going to equal minus 1/2 mv initial squared. Right. We're after the coefficient of kinetic friction. We don't know the mass of the chair. Fortunately, it shows up on each side of this equation. If I multiply both sides by -1 and divide out those masses, I'll get mu sub k gd is equal to 1/2 v initial squared. Do a little bit more work, solve for mu sub k. Mu sub k will equal v initial squared divided by 2 times g times d. So we can just plug in numbers here and figure this out now. We know the initial velocity, 3.05 meters per second. Square that, 2 times 9.81 meters per second squared times 2.16 meters. Now usually we won't get to keep three significant figures on a coefficient of friction, but in this case we do. Unit-wise also, meters squared per second squared on top. On the bottom I've got meters per second squared times meters, which will also give me meters squared per second squared. That divides with the same thing on top, and we get a dimensionless coefficient of friction, as all of them are. So in this case we'll end up with 0.220, or maybe a little bit of uncertainty on that last digit there. It could be 19 or 20, but about that. So we just used the work-kinetic energy theorem to figure out a coefficient of friction. And so, key thing, the net work was the change in kinetic energy, and the net work in this case was negative, the frictional force times the displacement. The next problem. If it takes 4 joules of work to stretch a Hooke's law spring 10 centimeters from its equilibrium length, determine the extra work required to stretch it an additional 10 centimeters. Just going to do a quick review of Hooke's law here. That's when you have a spring or something that exerts a force that looks like minus kx, and if you graph that, you get a straight, get a straight line that goes through the origin, and the slope is equal to minus k in this case. K is the spring constant. It's a measure of how hard a spring pulls back for every unit of stretch that you happen to give it. Now, we figured out that the work done by a spring is negative. If you stretch it, the spring will be opposing that stretch the entire time. You're pulling it this way and the spring's pulling back, and negative work is indicated by an area that's below the x-axis. This is the force, and that's the x-axis. If you compress it, then your displacement is going in that direction, and because you've got a negative displacement and a positive value above it, you'll end up with a negative amount of work there. However, this question states that it takes 4 joules of work to stretch that spring. So we're looking at the work that is done by the person acting on the spring, and they'd have to exert a force with a slope of plus k to stretch the spring by some amount. You have to pull in the same direction as the displacement, and you'll get a positive amount of work that you would have to do to stretch that. So that's what's going on here. Now, we're told it takes 4 joules of work to stretch it from 10 centimeters from its equilibrium length, and the extra work to stretch it an additional 10 centimeters. Well, here's what we can say. In this case, the work that we have to do will be 1/2 kx squared. We're told that if x is 10 centimeters, and by the way, I'll convert that into meters. This conversion factor is exact. We'll end up with 0.100 meters for the amount that we stretch it by. And we don't know the value of k, but we can figure it out here. 4.00 joules is going to equal 1/2 times k times 0.100 meters squared. And if you solve this for k, multiply by 2, divide both sides by 0.100 meters squared, you'll find that k is equal to 8.00 times 10 squared newtons per meter. Actually, for starters, you'd end up with joules per meter squared, but a joule is a newton meter, and you'll end up with a spring constant of 8.00 times 10 squared newtons per meter. And you should convince yourself that this is equal to this. There's also other ways to write the spring constant in other combinations of units as well. But you'll be working back and forth between 1 joule equals 1 Newton meter, and also something else you should keep in mind, 1 Newton is 1 kilogram meter per second squared. And a joule is also a kilogram meter squared per second squared. So all of these things get familiar with. I would just expect you to know those things off the top of your head. We just figured out the spring constant, but the question asks, determine the extra work required to stretch it an additional 10.0 centimeters. Well, the other day I figured out for stretching a spring from some initial position that wasn't its equilibrium position to some other position, the work required ends up being this: 1/2 k x final squared minus 1/2 k x initial squared. Okay, well, turns out this 1/2 k x initial squared is the 4.00 joules, and we're interested in what we have to do to get that. Except, well, we can go ahead and plug in the numbers now that we've got them. 1/2 times k is our 8.00 times 10 squared. In this case, since I'm going to be multiplying it by something in meters squared, I think I'll write it as joules per meter squared for the spring constant. We have lots of different versions, but that one will work. And then I'll be multiplying that by x final. Well, an additional 10 centimeters is going to be x final. We'll put this out here at 20.0, whoops, not 20.0, 0.200, cross that out, meters, and we square that, and then we'll subtract away 1/2 k x initial squared. You could do this process again, except that we know that's 4.00 joules. The additional work will be this. If I plug in the numbers on this expression, I get that this would be 16 joules minus 4 joules. It tells me the additional work would end up being 12.0 joules. Now, let me show you that solution graphically, and you might be surprised at how easy that thing turns out to be. Come back to this sheet of paper here. I'm just going to make a fairly accurate graph in this case, or more accurate than most of mine are. Usually I just sketch them very quickly. And this will be the force exerted by the spring, and this is going to represent the 10.0 centimeters. And then I'll have another one over here that represents the 20.0 centimeters. The slope of this is the spring constant. That's the 8.00 times 10 squared newtons per meter. Now, for the first part, they told us that this area right here, that's the area under the force we exerted versus position graph, that area is equal to 4.00 joules. Well, if I draw a horizontal line up here, this area right here is exactly equal to that one. And if I connect the diagonals of this little rectangle I've got down here, this area and that area are equal. It's a rectangle and the diagonal, but this area is exactly the same as that and that. So this is 4.00 joules here, 4.00 joules here, and the extra work to stretch that thing another 10 centimeters is 4 and 4 and 4. That's 12 joules. That's what we just got for this thing. That's another way of thinking of that extra work that we had to do to stretch that an extra little bit. Okay, we haven't done any power problems yet, but let's do this one. We have a 792 Newton Marine in basic training, climbs a 10-meter vertical rope at a constant speed in 8.00 seconds. So, what is his power output? Well, power is equal to the rate at which work is done. And so for power, if it's average power, you'd take the net work that's done and divide it by the amount of time that it takes for that to happen. We're told that he climbs at a constant speed. If that's the case, he would have a constant power output, because for every little increment of time, he'd be climbing the same vertical direction. Now, net work is going to be the force that he is exerting and times whatever the displacement happens to be. Well, we're told that he climbs 10 meters. If we make a little free body diagram here, here are the forces that are going to be acting on the climbing marine. We have mg downward, and he's going to have to exert an upward force on himself, kind of, and it'll just be upward in that direction. If he climbs at constant speed, he's not accelerating, then that force will have to equal the weight, and the net work in this case will equal this force, which is equal to his weight, times the height that he climbs, or the displacement that he climbs. So mgd is the net work. We're told that for him, mg is 792 newtons, so 792 newtons times 10 meters of displacement, and we get 7920 Newton meters, but a Newton meter is a joule. So the net work is 7,920 joules. Okay. But what's the power output? Well, the power is that net work divided by the time it took to do it. So the power in this case, 7,920 joules over 8.00 seconds, and I get about 990. Now, this W stands for watts. Work written out, it looks like that. Got to be careful on these. We use the same unit for the power unit as we do for work in this case. But at any rate, 990 watts is quite impressive for climbing something. Usually your arm muscles aren't all that strong. By comparison, 1 horsepower is equal to about 746 watts. It's not too hard for a human being to produce 1 horsepower for short periods of time if you're using the largest muscles in the body, which are the muscles of your legs, your quadriceps, but it's pretty tough when you're using the muscles in your arms to do that. So this is quite impressive. Another power problem here, this one having to do with something maybe more familiar. I'm not familiar with climbing ropes that fast for sure. But for a car with a mass of 1,600 kilograms, goes from 0 to 62 in 6.5 seconds, what is the average power delivered by the engine? Well, we can figure out the net work in this case. The net work is going to equal the change in kinetic energy, 1/2 mv final squared minus 1/2 m V initial squared. V initial is 0, so that second term there vanishes. Now the only bad part is we have to convert 62 miles per hour to meters per second, and so V initial or V final is going to equal 62 miles per hour times our, I'm just going to round to 2 sig figs, 1,600 meters per mile. That's an hour. Times 1 hour over 3,600 seconds. And we end up with 28 meters per second. So there's our final velocity. So the net work will just equal 1/2 the mass, 1,600 kilograms, times our 28 meters per second squared, and that ends up being 6.3 times 10 to the 5th kilogram meter squared per second squared. That's a joule, so we get that. The power, it's done in 6.5 seconds, so power is the net work divided by the time interval. 6.3 times 10 to the 5th joules, 6.5 seconds. A joule per second is a watt, and we end up with 9.6 times 10 to the 4th. This W stands for watts. I'm going to try to be careful when I'm talking about work to write a W sub net on it, so we know that. But anyway, that would be 96,000 watts, or 96 kilowatts, although this is just as good an expression as that one. But you sometimes hear the term kilowatt, often do in fact. The solar panels on our roof, when we look up how much power they're generating, we're told that it's some number of kilowatts. Those are the units that are most often used for that. When riding at 10 miles an hour, a cyclist uses food energy at a rate of about 400 kilocalories per hour, above what is used when standing still. And a kilocalorie is a food calorie, or a nutritionist's calorie, 4,186 joules. So when you eat that 100 kilocalorie, actually most candy bars are about 250 kilocalories. You'd take that number and multiply it by 4,186 joules and get something impressive. All right, walking at 3 miles an hour requires about 220 kilocalories per hour. And again, what is used standing still? In this case, you're transforming energy from one type to another. Food energy into energy of motion, work that you're doing against air resistance and all sorts of things. But you're transforming energy from food energy into some other form. That's the rate at which you are doing that is another form of power. And when we look at this, that 400 kilocalories per hour, or 220 kilocalories per hour, this is a unit of energy, that's a unit of time, this is actually a power. And so that's what we're talking about here. Now, it says compare these values with the energy consumption required for travel by car. Gasoline yields about 1.30 times 10 to the 8th joules per gallon. But let's consider what most of the time when we talk about cars, we talk about miles per gallon. And so gas mileage miles over gallon. Okay. Well, that gallon, we could call that a joule per gallon. And so we can replace it with that, and we would get, well, actually what I'll do is multiply this by 1 gallon, sorry for the messiness, over 1.30 times 10 to the 8th joules. And what I would end up here with is miles over joules with the energy on the bottom. And if we had a speed for this thing, we could convert these miles into some unit of time. And the gas mileage actually ends up being like the reciprocal of the power. So it's got the energy on the bottom. So let's go ahead and try to figure out what this might be if we convert it into units, into those sorts of units here. So for the walker, we'll take our 1 hour, I'll put that on top, and our 220 kilocalories. So basically I took my 220 kilocalories per hour and just flipped it upside down here. And then I'll multiply, I'll get some better units. I'll have 1 kcal over 4,186 joules. So now I've got it in terms of hours per joules. And then I'll convert that into some number of gallons. So 1.30 times 10 to the 8th joules per gallon. Okay, now I'll have gallons on the bottom and I'll have joules on top. Actually joule hours, but I want to get rid of those hours, so I'll multiply by the speed I was going at. 3.00 miles per hour, and the hours go away, the kilocalories go away, the joules go away. This ends up being just a weird unit conversion problem, very weird. And I'll end up with miles on top and gallons on the bottom. And when I do that for the person who was walking, I'll get 420 miles per gallon. So that's the equivalent energy consumption, or the distance that can be traveled for a gallon of gasoline's worth of energy. Actually, that's a whole lot of energy for a walker. Well, that's pretty darn good. You can't beat that with a car. But let's go ahead and do it for the cyclist as well. This is the walker. For the cyclist, I'll have 1 hour over 400 kilocalories. And then I multiply by the same batch of things. So that part I'd copy, except the cyclist is going at 10 miles per hour. 10.0 miles per hour. Same weird unit conversion thing. And for the cyclist, we end up with about 780 miles per gallon. So that's the equivalent energy use for a cyclist. That's not bad.